Apart from the halo, little else in a galaxy is spherically symmetric. The disk is essentially flat, and the bulge is ellipsoidal in shape. Elliptical galaxies are mostly bulge, and thus also ellipsoidal. Irregular galaxies come in any shape, and for those, the potential should be derived numerically. Let us consider here the potential for disks and ellipsoidals. With these three, spherical, ellipsoidal, and flattened, we will have the potential of the three components of a spiral galaxy, the halo, the bulge, and the disk, and we can then compute the orbits of stars with reasonable realism. In general, non-spherical systems are much more difficult to handle. Still, we can solve some simple and astronomically interesting cases. Let's solve first the case of an infinite sheet, the infinite disk with infinitesimal thickness. That's a simple model for a stellar disk. It's an infinite sheet of mass with constant surface density sigma. Now, because of the plane symmetry, the only non-zero component of the acceleration is in the vertical direction. So the vertical direction is here in z. You have this Gaussian surface, and we can then use Gauss' law to find what the acceleration is. So Gauss' law then would be the integration of gravity over the surface. So the surface is the surface of the Gaussian surface, and it's only the vertical one here, so we can substitute this by gz. And that is going to be equal to minus 4 pi g times the mass enclosed. Well, the enclosed mass is sigma times delta A. That's where it intercepts here. So we can substitute this mass. For a constant acceleration, we can take gz out of the integral, so it becomes an integral of the areas. Now it's gz times the two areas, the upper and the lower one, so twice the area, which leads then to the acceleration gz. It's minus 2 pi g sigma. Or in vector notation, we have minus 2 pi g sigma n, where n hat is a normal to the surface. That is, it's equal to z if it's above the plane, and is equal to minus z if it's below the plane. So we can write this compactly as gravity then is equal to minus 2 pi g sigma z over the modulus of z. So that will have the sine of z. So we can integrate this now to find the potential. So the potential is going to be 2 pi g sigma times the modulus of z. So let's now plot this potential and the acceleration. There you go. Right, so this is the potential of the infinite plane. You have here a linear potential above and below the plane. The abscissa here is the z direction. And the acceleration, see here, is positive below the plane and negative above the plane. Now let's find the same result, but by the Poisson equation. Then consider that the density distribution is going to have now a Dirac delta, right? The density sigma times the Dirac delta, because we only have mass here in this plane. So we can write the Poisson equation for this. It has now this Dirac delta, and we can expand the Laplacian. We have now a term that contains a derivative in radius and the derivative in the vertical direction, and the Dirac delta on the right-hand side. Now, because the very flattened distribution, the left-hand side is dominated by the z term around the midplane. That's where most of the variation happens. So we can ignore the radial term and write the Poisson equation with only the vertical term, approximating that by the right-hand side. Now, I want to make a pause here because this is a very important insight that applies to almost any thin disk. Even if the density varies in radius, the vertical variation in a flattened disk is so much more extreme that it's going to dominate the potential. We integrate now this equation twice in the z direction. So we integrate on both sides in z, and the integration in the right-hand side removes the Dirac delta. So we have simply 4 pi g sigma on the right-hand side now. If we integrate now the left-hand side, again, we have to see that most of the contribution arises from the region around z equals 0. So let's integrate then the left-hand side in a small region around the midplane, going from minus z to z. And this integral gives you then the first derivative of phi. So that's in the limit here z, and the second term here in the integration limit minus z. Now, because the potential is symmetric, as we see here, phi of minus z is equal to the phi of z. The potential minus z is equal to the potential of z. So this here becomes twice the derivative in z of the potential of z. So we have a simpler equation, and we can integrate again to find the potential of z.